Today, we're going to talk about something called traveler point dynamics. Now, stick with me here, because it's this really cool way of looking at the universe, a kind of toolkit that promises to make some of the trickiest ideas in physics feel, well, surprisingly simple. So yeah, let's dive right in. Okay, so what if I told you there was a kind of secret toolkit that makes Einstein's physics feel as intuitive as, say, Newton's? What if we can make something like relativity feel as natural as just throwing a baseball? That's the huge promise behind what we're talking about today. And, to really get why we even need a toolkit like this, you've got to understand that modern physics, it kind of feels like it's running on two totally different operating systems at the same time. So on the one hand, you've got your everyday physics, Newton's laws. This is the stuff that just makes sense to us. Cars, baseballs, falling apples. It's intuitive, it's familiar. But then, for the really extreme stuff, like black holes, the speed of light, or even how the GPS in your phone works, we have to switch over to Einstein's relativity. And that can feel incredibly complicated and just plain weird. It's almost like having one set of rules for when you're walking down the street and a completely different, much crazier set of rules for when you're flying in a jet. And this is exactly where this new approach, this traveler point dynamics, comes into play. It gives us a toolkit that kind of brings these two worlds together. And the secret is, it focuses everything on the perspective of a single person, a single traveler moving through space-time. So let's go ahead and open up this toolkit and see what's inside. Okay, first tool in the box. Proper time. Now, this is a big one. Forget about a master clock on Earth or anywhere else for that matter. Proper time is the time that ticks by on your clock, on your own wristwatch. It's your personal, totally unique experience of time. And it turns out that's probably the most fundamental measurement we can even make. All right, next up we have proper velocity. So instead of measuring your speed against some, universal clock way off in the distance, which is what physicists call coordinate time, we're going to measure it against our own proper time, the time on our own watch. And what's super interesting here is that when you measure velocity this way, it connects directly to an object's momentum.
And this leads to a really wild idea. We all know nothing can go faster than the speed of light, right? That's the cosmic speed limit, c. But that's coordinate velocity. Your proper velocity, measured by your own clock, well, it has no upper limit. None. So from your own perspective, the more energy you pour into moving, your momentum and your proper velocity can just keep climbing and climbing forever.
And the last main tool in our kit is proper acceleration. Now, this isn't some abstract math concept. This is the real deal. It's the acceleration you actually feel. It's what the little accelerometer inside your phone measures. It's that G-force, that push you feel in the back of your seat when a car floors it. That's proper acceleration. Okay, so we've got our toolkit, right? It's all based on what a traveler personally sees, feels, and experiences. So let's see how this helps us make sense of the forces all around us. Specifically, how it helps us separate the forces we feel from the ones we don't. So let's try a little thought experiment. Grab your smartphone, or just imagine it. It has an accelerometer inside. Now, when you're just holding it still, that little device inside is reading about 1 g of force. That's not gravity, that's the force of your hand pushing up, stopping it from falling. But what happens the second you drop it? The moment it's in freefall, the reading on that accelerometer drops to 0. So why is that? And this is where it all clicks. The source material explains that gravity is a geometric force. It's not a force in the way we usually think of it, like a push or a pull. No, it's actually the shape of space-time itself that the phone is moving through. And because gravity is acting on every single atom of that phone at the same time in the same way, the accelerometer inside doesn't feel a thing. It's not a proper force. So this leads to a really important split. You've got proper forces on one side. These are the forces you feel. The push from a rocket engine, the pressure of your hand holding your phone. These are the things an accelerometer can actually detect. But then you have geometric forces on the other side, things like gravity or even centrifugal force. An accelerometer is totally blind to these because they're not really forces on you, they're the properties of the path you're taking through spacetime. They are essentially the unfelt forces. Okay, now that we have this toolkit, we can start to unpack some really, really wild puzzles. Let's jump into a kind of sci-fi scenario that comes from the source paper. It shows just how powerful and, frankly, how strange these ideas of proper time and proper acceleration can be. All right, picture this. There's a starship. It's on this long, long journey. Suddenly, they spot an enemy ship. They decide they have to intercept. So they fire up the engines, make this huge high-acceleration maneuver that takes them way off their original flight plan. Now, this whole detour, from the moment they break off course to the moment they get back on it, takes them exactly 4 years, according to their own ship's clocks. Now, common sense says this detour had to have cost them time, right? I mean, it's a detour. Nope, wrong. And this is just incredible. After that 4-year detour is over, the crew checks their clocks, they check their mission calendars, and they discover they've arrived back on their original path 4 months ahead of schedule. Think about that. The specific path they took through space-time, the one with all that intense acceleration, it actually made less proper time pass for them. They took a 4-year detour that literally saved them 4 months. So, what does all this mean? Why is this traveler-focused way of thinking about things more than just a cool sci-fi puzzle? Well, it's about building a much more unified and much more intuitive picture of the entire universe. I mean, the implications here are pretty huge. For one, it could totally change how we teach relativity, giving students a way to actually feel it instead of just doing the math. It also gives real, practical tools to engineers. People designing GPS systems or planning for future spacecraft, they need this stuff. And best of all, it finally really bridges that gap between Newton and Einstein. It shows us that Newton's laws are not wrong. They're just a really good local approximation inside this bigger, traveler-focused picture. And that leaves us with one last kind of mind-bending thought to chew on. We've just seen how the path you physically take through space-time, your literal trajectory, directly changes how you experience time itself. A detour can save you months. So, if our physical path through the universe can shape our experience of time, what does that say about all the other paths, all the other choices we make in our lives? That's something to think about.